So I already did the analytical solution for the electric field due to a charged rod. So, and what we mean by that, there's like a stick here, or you can think of it maybe I take a pen and I rub it with plastic and I put it there, and so it's uniformly charged. There's positive charge spread over the whole thing, and I wanted to find the electric field at some location X on the x-axis that's centered in the center of that rod, and that is important. And so I did that calculation already, and the video link to that will be down below. And the result was I found that the electric field is only in the x direction, and it has a value of 1 over 4 pi epsilon naught. That's at Coulomb constant. The total charge Q divided by x, this distance, times the square root of x squared plus L squared over 4. Now, but there's another way to calculate something like this, and that's with a numerical calculation. Remember what we did well, maybe you haven't seen it yet, then you should go watch that video. But what I did was to take this rod, since we don't know how to find the electric field due to a rod, we do know how to find the electric field due to a point. And let me show you that real quickly as a review. So if I have some charge Q1 right here at the vector location R1, and I want to find the electric field at some point over here, the observation point, I call that RO, then the electric field due to that point is 1 over 4 pi epsilon naught Q1 over R squared. So R is the vector from Q1 to the observation location. You can find that with this. It's just a difference in vectors times the unit vector R hat. In the analytical solution, I broke this into points. I broke this into pieces. And I'm going to do that again. But in the analytical solution, I took the limit as the piece size goes to 0 and the number of pieces goes to infinity, and that turned into an integral. And that's how I got this. So we're going to do that again. We're going to break this into pieces, but we're not going to break it into an infinite number of pieces. We're going to use a finite number of pieces. So let's just do that. Let's break this into, let's see if I can do this. 1, 2, 1, 2. So here I broke this into 1, 2, 3, 4, 5, 6 pieces. So I can say n equals 6. Now each of these pieces I can treat as though they are a point charge, which is not true, but that's fine. Okay. So for each of these pieces, I need the location. Let's call this one down here R1. So I need the location of R1, which would be this vector. And I need the charge there. Well, the charge is pretty easy. I can say delta Q equals the total charge Q divided by N. Now, this is a numerical calculation. What I'm going to do is to calculate the electric field due to each piece and then add them up as vector numbers. And so that means that everything has to be a number. That's why this is called a numerical calculation. I can't get an expression for the electric field. I get the answer of the electric field. And you may think that's not cool and everything, but everything that we do is essentially a numerical calculation anyway. When you do any type of trig function, that there's no easy way to get that without either having an infinite series or a lookup table or something like that. So I'm going to have to use numbers. So I have the charge of the rod is Q, the length is 0.5 meters, and this x distance is 0.03. Now what about the vector? Let's find the vector location of R1. So down here at the bottom, and we can just deal with the y direction here because the x and the z components of that R vector are 0. The y value down here is negative L over 2, right? Because if this whole thing is L, and from here to there is L over 2, then this would be negative L over 2. And I actually could use this point as the location of my value, but I'm not going to. I want to use this piece right here. So I need to know what's the length of this whole thing right here. And let's call that delta y. So delta y is going to be equal to the total length divided by n. Right? So if I divide this into 6 pieces, then each of these pieces has a length of 1/6 the total length. Now I need to shift up a little bit, right? So I need to shift up half of the length of delta y. So that means y1 is going to be negative L over 2 plus delta y over 2. So delta y over 2 will shift that from this bottom up just a little bit. And again, if I had 10,000 points, it doesn't really matter if they're shifted a little bit. You'll get a very good answer. But I just want to do this the right way because I feel like that's something I should do. So that's my first location of my charge, and I know my value. Then I just need to find this vector, right? Which I know if the observation location, I know I know both of these. Let me write them out explicitly. So R0 is going to be x0, 0. So that's 0.03. R1 is going to be 0, negative L over 2, plus delta y over 2, 0. And I know delta y because I can calculate that. It's a number. And then I can calculate R, and I can calculate the electric field because I know the charge there too. Now what about the next point? I need to find the next point up here. Well, that one's not so hard because if I know the location of this piece, I know this one is shifted up delta y. So R2 is going to be equal to 0, y1 plus delta y, 0. And then I can repeat the whole thing again. So I'm going to find the electric field due to this charge at this point, the electric field due to this charge at this point, and so forth, and add them all up, and that will give me my total electric field, and I can compare it to that. Okay, so we're going to do this in Python. If you have 6 values, you could actually do this by hand. A numerical calculation does not mean that you have to use the computer. It just means that you're using breaking this into smaller pieces and using numerical values. Now, if I want to break this into 6 pieces, not so bad. If I want to break this into 1,000 pieces, bad. Okay, I don't want to do that 1,000 pieces. So I'm going to do this in Python. So let's switch over here to Python. So if you haven't seen this is trinket.io using GlowScript vPython. GlowScript vPython is really nice because it's online, and so you don't have to install anything. And 2, here it has a vector class built in, so we can use vector operations, and that's super cool. So let's just start adding in some of our constants here. K equals 9 times 10 to the 9th. Let's make that a little bit bigger. Is that big enough? So this is the 1 over 4 pi epsilon naught. I'm just going to call it K. I'm using numbers, so I don't want to put in the units. If you want to put the units as a comment, you could. Newtons times coulomb squared. Sorry. No, meter squared. Meter squared per coulomb squared as a comment. That's fine. I need the total charge Q is 2 nanocoulombs, so 2 times 10 to the negative 9th. I need the length, 0.05. And then I'm going to call this XO. I think I'm going to call it X. No, let's call it XO. X equals 0.03. That's all I had right to start with. Okay, so now I'm going to do this. N equals, I'll do 6, and then we'll change it. N equals 6. dq equals q over n. I'll call it dy equals L over n. That's just like I said before. I'm using D instead of delta because there's not a good way to type delta, and I don't want to type out delta because I'm lazy. Okay, so now I'm going to make a loop. I'm going to make each one of these things, and there's a lot of ways you could do this. You could use a list of points. You could even visualize it, and I will do that in the very near future. But I want to make this as easy as possible that makes the most sense. So the first thing I'm going to do is start off with my observation location. So I'm going to call this RO equals vector XO, XO, not 0, 0, 0. And so that's a vector in Python. I can print that just so you can see it is indeed a vector. If I run this, it will print it as a vector, and that's kind of cool. Okay. So the next thing I'm going to do is to create my electric field. So I'm going to calculate the electric field due to each of those pieces and add it to the total, but I need to start off with the total. So the total to start off with is going to be 0. So I'm going to say E, oh, what the heck is going on? E equals vector 0, 0, 0. So there's no electric field, but I need to start. I can't add something to nothing. I have to have something there. So that's my electric field to start with. Now I'm going to do this. I'm going to say RQ. Let's call it RQ. That's the location of the charge. I know my starting location. It's going to be equal to, I already said this, vector 0, negative L over 2 plus dy over 2, 0. That's my starting location. Now I can do the following. What I'm going to do is calculate the electric field due to that piece, and then move up a piece to the next part, and keep doing that until I get to the top. So I'm going to say while RQ dot y, the y component, I can't do this with the whole vector, is less than L over 2. Do everything in this loop. So this is a loop, but I'm going to do it until I get to that top part. Oh, this is L over 2 minus dy over 2. And I think that might work. It might not work. We'll check it real quick, though. So the first thing I'm going to do is to calculate the vector r from my point charge, which I'm calling RQ, to my observation location. So I can say R equals RO minus RQ. Now I can calculate the electric field due to that little piece, which I'm going to call DE because it's not the whole electric field. And it's going to be K times DQ times norm R. So norm returns a unit vector in Python. If I whatever vector I put in there, it gives back r hat. That's r hat. And I also have mag r, which is the magnitude of r. And I need to square that, so that's star 2 in Python. So that's the electric field due to that first little piece. And now I'm going to add that to the total, E equals E plus DE. So now I need to move my point charge up one piece. So I'm going to say RQ equals RQ. Let's move this up a little bit. Plus vector 0 dy 0. So that's going to move it up. Eventually it'll get to RQ has the L over 2 minus dy over 2, and that should work. And then that's it. So we can print this out, print out the total electric field. E equals E newtons per coulomb. And I'm gonna show you that things are working. Let's just run this first. So there's my electric field. Remember I said in my analytical calculation that the y component would be 0, and you see here that the y component is not 0. It's 2 times 10 to the negative 13th. Okay, so that's just a rounding error from the square root and stuff like that. So it's basically 0. And then I get 1.5 times 10 to the 4th, and that's cool. But do we actually have 6 points? Let's just do this. Let's print out. I have RQ before I update it. Well, let's print out my starting RQ. So let's just print RQ. Let's print RQ.y. I don't need the whole thing. And then down here, after I update it, I'll print out RQ. No, I'll print it out right here. No, it should be down here, because that'll give me the same thing. Print RQ. Okay, let's see if we get 6. Okay, so I printed out RQ.y. Let's just print. Okay, let's change that. Okay, so I have. Ooh, I got more than 6, didn't I? 1, 2, 3, 4, 5, 6, 7. Okay, so this should be. I actually printed out 1 too many, because the last RQ should be. Let's print RQ last equals. What would it be? It'd be L over 2 minus dy over 2. So my last I got here is 0.29, and this should be 0.2. So I got 1 too many. So if I can change this by saying while RQ is less than, let's see, so what would I do to get rid of that last piece? Well, I could change this to dy. While it's less than this number, right? Because now I'm actually going to move past that, and it won't print it. I think this will work. Yep. Okay. So it only did 6. So 1, 2, 3, 4, 5, 6. That's 6, right? I can't count. 1, 2, 3, 4, 5. Well, no, it's 5. 1, 2, 3, 4, 5. I definitely did 5. Okay, I had it right before. Minus dy over 2. I just have a counting problem. That's what I'm having. No, that's wrong. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. That is 6. But my last one should be, so L over 2 is 0.25. See, so that's past it. I mean, the answer is I'm gonna figure out this error later, okay? And it's a bad error, but if I have one extra piece and I have 1,000 pieces, it doesn't matter, okay? So I'm just gonna get rid of these. I made a mistake. This is the second time I made this video, and I made a mistake the first time, and so I don't want to redo it again. Let's just change this to 50. And there's my electric field, 1.5 times 10 to the fourth. That's pretty small, but it's not 0, and that's okay. Let's change this to, now let's change this to, let's just change it to this. Okay, I'm happy with that. Very small, that's right. Now, if I increase this to 500, we were looking to see if this changes significantly, that x component changes significantly, and it doesn't. So you can see as we increase more and more and more points, we're still getting about the same thing. That indicates we're probably on the right track. But let's do the following to really show that we're on the right track, and that is to calculate the theoretical value of the electric field. So I'm going to say ET for theoretical is going to be K times Q, right? This is from my analytical expression. XO times the square root of XO squared plus L squared divided by 4. And let's print that. Print E theory equals, it's for the analytical, ET, and then put the units, newtons per coulomb. And let's run that. And you'll see here, this shows us that we're right. Look at that. These two numbers are very close to each other. And in fact, even if I go down as low as something like 10 units, 10 pieces, I still get pretty much the same thing. It still works. So I don't even need to do 1,000 data points, but I can break this into 1,000 pieces easily right there. Okay, and then it's kind of like still a numerical expression, because I can go up here and change the length or the charge or x, and everything would work. Now I want to show you one more thing. Let me switch over to the paper, because this is something that shows how powerful this is and why you do it, not just to check your answer. So if I go over here to the paper, now imagine that I want to change my observation location. If I have it anywhere on the x-axis, then this formula still works. But what if I want to be like right here? So now here is RO. This equation doesn't work because this made some assumptions about the way everything was distributed and the way I set up the integral, and it's just going to be a different expression. But my calculation numerically it doesn't matter where RO is. In the numerical version, I can have RO wherever I want. So let's pick RO equals, let's see, 0.02, 0.030 meters. And let's just change our program to put this as my initial observation location and see what we get for the electric field. So I'm switching back to the computer. I don't need to change anything, right? I have here the vector observation location that I'm starting with. I just change that to whatever I want. So I'm just going to put this at 0.02, 0.03, and now I'm going to run it. And you'll notice something really important here. I get a different x component, which kind of makes sense. I'm a little bit closer, but some of those electric fields are much actually further away and they don't push in the x direction as much. But my y component's not 0. And so this is the legitimate expression for the electric field, the numerical value for that electric field, even though it's not an analytical expression. And that's what shows you why this numerical calculation is so important. I can calculate the electric field anywhere for this case. Now, there is another thing I want to do, and that's to make a visual representation of the electric field around this charged rod so we can actually see what it looks like. And we're going to use some other features of VPython, GlowScript VPython for that, but I'll make that in another video, so I'll stop here. And the code will be down below. The link to the video, the previous video will be here, so you should be good.